Hi, it's Mr. Benson here with solutions to the probability example we did in class on Thursday. Now, we're going to do a test on this next Wednesday, so I'm going to prepare a few resources for you to refer to when you're at home. So onwards. So this is the one where we had the class that I'm really fond of, and I'm giving some presents to the students at the end of the year. So we've got a few bits of information we have to be careful with when we're thinking about questions like this. So one of them that we always need to keep in mind is how many students we have in total. So in this case, we've got 24 students. Another thing that we've got to be careful of is words like only that appear. So we've got 24 students in total, 3 receive nothing, 10 students only receive a box of angry wasps, so that's my event W there. The remainder receive a box of irritable racer snakes, which is our S event, but 8 do receive both gifts. So these are sort of bits of information we need to come back to later on. Sorry, it might be, you might find yourself maybe wanting to wind back bits of the video to look at things that I've done on previous slides as we're going through this. The first thing that we're asked to do, and this would be a sensible thing to do in any case, is to represent your data in a way that helps you think about the probabilities. And so a Venn diagram is a good choice for this, or you could do the two-way table first, really depending on what your favorite is. I would probably suggest the Venn diagram just because that's what we're, you probably had more exposure to, but you see that really the two things are the same. So I've got my universal set is 24 students, and yes, I am writing it outside the box, but that's because I don't want to get confused about my numbers. Now I know as well that I've got two sets, and I know that they overlap because there are some students who get both, so I'm going to draw these two circles overlapping. One of them is snakes and one of them is wasps. Now the first thing that I tend to do when I'm thinking about these is that the easiest things to identify are usually the intersection and also those items that aren't in either set. And so we've got 3 students who received nothing, and so they are going to be outside. Then we've got 10 students that we're told received a box of angry wasps only. So the only tells us that they are in W but not also in S, so they've got to be here. Now the remainder of students are getting the racer snakes, but we also have to think about which students get both gifts. And we're told that there are 8 that receive both, so they must go in the intersection there. And then all we've got to do is thinking about making our numbers up so that we've got 24. Because the total of all the subsets in the universal set has to add up to whatever the number in the universal set is, which in this case is 24. So if we've got 10 who only receive wasps, 18 who received wasps, 8 who received wasps and snakes, giving a total of 18 in the wasp set. 3 who received nothing, we're up to 21, so we must have only 3 students left who got only snakes. Then we're going to represent that in a two-way table. So remember, with a two-way table, we're talking about our 2 sets, but we're thinking about students who got snakes and students who did not get snakes on one axis, and students who got wasps and students who did not get wasps on the other axis. And then we're just going to fill our table in. Now, again, I tend to start with the things from the Venn diagram that are easiest to place. So the ones that are in the intersection here, so they're in both sets, are going to be in this spot on our two-way table. The ones that are outside of both our sets are going to be here because they're not in set S and they're not in set W. And then we just have to think a little bit more carefully about the other ones. Now, if we think about our 10 who only got wasps, so they are in set W but not in set S, so they have to go there. And then we're left with our last 3 who got snakes but didn't get wasps, and they're in this column, this first column. Now the last thing we want to do with our two-way table is just check that everything adds up, and also get some subtotals that are useful. So we've got 18 who are in set W, which means we've got 6 who are not in set W. We've got 11 who are in set S. We've got 13 who are not in set S, and we've got 24 who are in the universal set. So that's our two-way table, and this information will come in handy later on when we're doing our probabilities. So now that we've drawn our Venn diagram, we can start to calculate some probabilities. Now you can use the information from the two-way table or the Venn diagram as long as you really remember what you're looking at here, and either way will be fine. Now remember that when we're trying to calculate theoretical probabilities like this, all we're thinking about is how many ways we can get the favoured outcome divided by the total number of outcomes. And so the first question is the probability of a student getting nothing. Now there are 3 students who got nothing out of a total of 24 students, so that's 3 out of 24. Now in most tests and stuff, it is going to want you to simplify this, as I've mentioned numerous times, so you're probably bored. I think there is something to be said for leaving the denominator the same, because then it's easier to see, to actually compare your probabilities. Because if everything's out of 24, then it's just the numerator that determines the, the size of the probabilities. Okay, then the next one is the probability of W, so thinking about WASPs. Now if we're doing this from our two-way table, that's actually easier because we've already totaled up the number of people in W. But if we're doing it from the Venn diagram, we've just got to be careful that when we're saying the probability of W, we don't care about any other information. So it doesn't matter that these 8 people are also in set S. All that matters is that there are 18 people who are in set W, which means that when we're calculating our probability here, it's just going to be 18 over 24, which is 3 out of 4 is the simplest form of that. Then the next one. Now we've got to be good with our set notation when we're doing Venn diagrams. So we need to remember that this funky thing that looks a bit like an upside down U is the intersection symbol, which means we are talking about the things that occur in both sets. So another way of thinking about intersection is AND. So it means things where the snake event happens and the wasp event happens, so it's the people who receive both snakes and wasps. So all we've got to do again is carefully identify the right bits of our Venn diagram. So we can see that there are 8 people in that intersection there. Out of 24, again, gives us a probability of 1 out of 3 when we simplify that. Now going back to the thing I keep banging on about comparing probabilities is, when they've all got different denominators, like the stuff in this right hand column here, where we've got 1 over 8, 3 over 4, 1 over 3, it starts to become harder to compare them. Alright, more set notation. The U means union. Now union is everything that is in both the sets. So we need to think about everything that is in S and W, and it doesn't matter whether it's in both. Now this is not quite as clear actually off a two-way table, but all we need to do here is basically add up all the numbers here. So we're going to have the 3 that are only in set S, the 8 are in both that are in both sets, and the 10 that are only in set W, giving us a total of 21 out of 24. And so that would be 7 out of 8. And the last one, now this is me starting to get a little sneaky here, where we've got to think about this complement symbol. So the complement symbol means not that thing. And so, look, there's probably a few different ways you can think about this one. What I tend to do is just to basically think about what is not in that set. Now in this case, we're thinking about what's not S, and is also not W. Now, if we think about things that aren't in S, so what's not in S is that we have 3 people who are not an S or W, and we also have 10 people who are not an S but are in W. Then when we think about what's not in W, well, we have the 3 people who aren't in both sets again, and we have the 3 people that are in S but aren't in W. But then when we think about the only part of this that was in both sets, that is to say that's in not S and not W, is the 3 people who are outside of both sets, and so they're the people who receive nothing. And again, we're back to our original 3 out of 24, which equals 1 over 8. Then we get on to something which is a bit trickier again. So we've got the probability of S given W. Now there's a few ways that we can think about this one, and they both are perfectly good. They depend a little bit on the information that you are given. Okay, so looking again, the probability of S given W. So let's start off with thinking about it just in terms of the Venn diagram. So if we're doing that, then we don't really need to overcomplicate stuff, I guess. All we've got to think about is that we're saying the probability that S is happening given that W has happened. So what it means is we're limiting ourselves to part of our universal set. So we are limiting ourselves to the W set. And then we're thinking about, okay, given that W has happened, what's the probability that S is going to happen? So, well, then we can think about, well, how many ways can we be in set W? And so we're thinking about a denominator of 18, and we're going to have then thinking about how many ways that we can be in set S. And there are 8 things that are in set S and set W, so the probability of S given W is 8 over 18, or we can simplify that down to 4 over 9. Now that's the that's doing it from the Venn diagram. So just thinking about your favourable outcomes and all the possible outcomes and that kind of stuff, just getting the theoretical probability. But we can also use our formula, which is that the probability of S given W is going to be the probability of both things happening, so S intersection W, over the probability of W. Now, if you've already calculated the probabilities, or if you've just been given the probabilities, this might be a better approach. But yeah, if you've got the Venn diagram, probably go with the Venn diagram. Okay, so we've calculated some of these things previously. So the probability of S intersection W, so the probability of both events happening, is our 8 out of 24, which is, well, it's 1/3, isn't it? So that's nice and easy. So there's a 1/3 probability that someone in that class was going to get both of my fabulous gifts. Then the probability of W, that they were going to get the box of wasps. So we can see that we've got a total of 18 people in our wasp set out of 24 students in total, and so we get 3 out of 4. And then, now the only possible downside of this one is remembering how much everyone loves dividing fractions here. We've got to be a little bit careful. So the probability of S given W, so it's the probability of the intersection, which is 1/3, over the probability of W, which is 3/4. Now, remembering when we're dividing fractions, we go 1/3. Now I'll change colors here just to highlight what we're doing. Now we change to the multiplication symbol, and then we are going to invert our second fraction. So it goes from 3/4 to 4/3. And then what we get there, so when we're multiplying fractions, we just multiply the numerators together, we get 4, and we multiply the denominators together, we get 9. Same answer as our other technique. The last couple of questions, just really thinking a bit about stuff that can happen here, and there's lots of different answers, but the whole idea here is it's just getting you thinking. So identifying complementary events. So we've got to think about this definition of complementary. So complementary events are things which add up to the universal set, which also means that their probabilities add up to 1, and they are things that don't have anything in common, so they're all complementary events are also mutually exclusive. So all we've got to think about really here is two things that are not happening at the same time and add up to everything else. So for example, one group that didn't get anything, so not S intersection not, whoops, my bad, I meant to do a W there. So not S intersection not W, which is our lucky 3 people on the outside, that is complementary with everyone else, which we could write as S union W. Now, I didn't necessarily expect set notation here or anything. I just want you to think about the ideas. So these 3 people here, the complement of that set is everyone else, which is the other 21 people, which is an S union W. So those are complementary events. So all you've got to make sure is that they don't overlap, so they are mutually exclusive, but they also must add up to the sample space. Then, when we're thinking about mutually exclusive events, it's just stuff that can't happen at the same time. So if we're drawing a deck of cards, you can't have, say, a red club. You can't have, or when you're throwing a dice, you can't throw, when you throw one die, you can't simultaneously get an odd and an even number. So those events are mutually exclusive. So all we have to do here again is just look at some things which don't overlap with each other, but also don't add up to the whole, or don't necessarily have to add up to the whole of the universal set, because things can be mutually exclusive without being complementary as well. So for example, we might have, again, we think about our people who didn't get either gift. So it's the 3 people who are not in set S and not in set W. And then we might think about the people who are in set W. So these 2 groups here are mutually exclusive events, but they are not complementary events. Okay, and then lastly we get to the extra nerdy question, and I'm definitely going to throw these harder ones into the test. So this is stuff that is definitely at a year 10 standard, but I've seen lots of you be quite comfortable with answering these sorts of questions, so I think it's quite reasonable to make these a part of the standard test. So the test here is that the probability of 2 things happening, if they're independent, should equal the probability of one thing happening multiplied by the probability of the second thing happening. Now, if you think about events that we are certain or pretty certain are independent. So say you toss a coin, you're going to have a 1 in 2 probability of getting a head, and then you toss another coin and you've got the same probability. And if you do an experiment where you toss 2 coins, you've got a 1 in 4 chance of getting 2 heads, which is 1/2 times 1/2. So that's a nice example of how that works with an independent or a couple of independent events. So we'll apply that test. Now we have to calculate these things separately, and we've actually done most of them already. So we're not really doing new work with most of these questions. So the probability of the intersection is just our 8 out of 24. I probably won't simplify these at the moment because it doesn't really matter that much. Then the probability of S, of getting the snakes, was 11 out of 24. And the probability of W, which was getting the wasps, probability of W is 18 out of 24. Which I will simplify slightly because that's going to make my life a little bit easier. So then when we do the test, so the test is just that we're going to multiply these 2 bits together. So we're going to go 11 over 24 multiplied by 3 over 4. Now actually I'm going to simplify my 3's there, and that will work. So that'll turn into 1 over 4, and that'll be 11 over 8. And that's going to turn into 11 over 32. And this is showing that these two events are not independent, so they are dependent, because this value here does not equal this value here. So in this case, what we're seeing is that the probability of S intersection W does not equal the probability of S multiplied by the probability of W up here. And so in this case, this tells that these events are dependent. And that, might be something that has a real life reason, or it doesn't really matter, to be honest, with the example, because you want to be proving these things mathematically rather than going with a hunch that something seems like it would be dependent or independent. Okay, I hope that's helped. I will also put up some other examples of things, because I realized what I didn't cover in this was things like the arrays and probability trees. That will be another part of the test next week. So I'll do some work on those for you as well.